In our earlier discussion, the atomistic viewpoint of matter was established in the 19th century with Dalton's atom-based composition model and visualization just as Descartes' Hooke model. With statistical mechanics, a particle perspective was provided to the phenomenological theory of thermodynamics. Still lacking was an understanding of the source of interaction. This brings us to the next part of our course, in which I will talk about the substructure of the atom and with it the non-classical phenomenon of energy discretization. We will see that the energy discretization on the atomistic scale is one piece to the puzzle on what makes the nanoscale differ from the macroscale. About half a decade after Dalton's atomistic theory, experimental indications solidified, suggesting the atom might not be well represented by an indestructible solid sphere as proposed by Dalton. Around 1830, Michael Faraday discovered that dissolved compounds in water accumulated at opposing electrodes that were placed in the solution. His observations that are comprised of the laws of electrolysis led Faraday to propose that atoms had an electric component. It took another 70 years until the beginning of the 20th century to perceive that the atom was built up of positive and negative charges. As we know today, it is the combination of these charges and their collective electromagnetic fields that give the elements the potential framework within which they aggregate and structure. Before I continue with the evolution of the atom theory, I want to point out that the resultant quantum theories are not solely based on the discoveries concerning the atom. Quantum mechanics and related quantum theories evolved also from the recognition of discrete patterns in the photon light spectrum of matter, the electromagnetic radiation surrounding a body in thermodynamic equilibrium with its environment, and the light quantum. One of the first steps towards an improved understanding of the atom substructure was provided by Thomson and Rutherford's discovery in 1897 that the atom contains electronegative particles known as electrons. About a decade later, in 1911, Rutherford deduced from scattering experiments the existence of a positive nucleus within the atom. Based on Rutherford's insight and the widely discussed discrete spectral lines in emission spectra of matter, Bohr proposed in 1913 his famous model in which he envisioned well-spaced orbitals on which the electrons move around the nucleus. In addition to the discretization of the energy levels, which is in contrast to the classical continuous view of energies, Pauli imposed in 1925 a limit on the numbers of electrons on energy levels, or sublevels. This led the following year to a thermodynamic deviating statistics known as the Fermi-Dirac statistics. Heisenberg recognized in 1927 with his uncertainty principle in energy and time or location and linear momentum that it is impossible to follow an electron on its trajectory. The same year, Schrödinger utilized de Broglie's concept of the dualistic nature of the electrons, that is, to behave like waves and corpuscular particles, and introduced the widely used quantum mechanical wave equation. Because of this deviating behavior of the electrons from classical physics, a new theory was born, the quantum theory. While statistical mechanics treats atoms in a Newtonian sense as corpuscular particles with deterministic location and momentum, within a continuous spectrum of kinetic and potential energies, quantum mechanics and its field theories consider the electrons more like a fuzzy particle that exhibits both wave and particle characteristics. Bound or in the vicinity of atom cores, electrons are attributed discrete energy levels. These classical deviating aspects have implications on the nanoscale. In order to describe the experimental results of Rutherford and his contemporaries, Bohr postulated a simple model with electron orbiting around a positive nucleus. The model states, electrons in an atom can only rotate in certain selected orbits around the nucleus and do not radiate energy. These orbits are stable and called stationary orbits. Each of these orbits has assigned to it a well-defined energy value. Emission of radiating energy is caused by discrete jumps of electrons from one stationary state to the other lower state. The energy and frequency of light emitted or absorbed is given by the difference between the two orbit energies. While Bohr's model oversimplified the situation, it was actually a lucky shot predicting energy levels for the electron in hydrogen correctly. It had tremendous impact on the early development of quantum mechanics. It provides a wonderful visualization on energy discretization. This brings us now to discuss the transition from the atomic scale to the macro scale. With the atom we have introduced discrete energy levels, or orbitals. In the ground state, the electrons occupy the lowest energy states, visualized here in blue and labeled occupied orbitals. Atoms can covalently bind together to form electrically neutral molecules by sharing their electrons. Considering multiple atoms or molecules, we distinguish between condensed phases in solid or liquid form and gas phases. Which phase develops depends on the strength of the interaction between the atoms or molecules and their kinetic energy. In solids, atoms and molecules are either arranged in regular crystalline structures or irregular amorphous structures, or a mix of both. Small aggregates with diameters on the order of a few nanometers are called clusters. Atom clusters still exhibit discrete energy states that are more dense and more plentiful than in atoms. By increasing the size from the single atom to the cluster and beyond, the energy levels densify further until they appear like continuous energy bands. Here depicted are the electron-filled valence band and the empty conduction band. Overlapping bands signifies the special case of a metal conductor. Thus, while in nanoscale systems the energy levels are still discrete, in a macroscopic system the energy levels are indistinguishable. This has tremendous effects on properties such as electron conduction, which we will discuss later. But let's first turn briefly our attention to the gas phase. We consider the size of the system d, within which the gas molecules are contained. To describe an ideal gas with classical statistical mechanics, the system size has to be significantly larger than the so-called mean free path xi of the gas molecules. The mean free path is the average distance of a gas molecule to move undisturbed without scattering at obstacles. At ambient condition, the mean free path of the molecules within air is around 70 nanometer. For a system size d on the order of the mean free path, scattering at the wall will become prominent and consequently affect the gas properties. In a cube with a size dimension of 70 nanometers, there would be around 3000 air molecules left, significantly less than the Avogadro number. At such low numbers, property fluctuations are large and equilibrium conditions questionable. In the macroscopic bulk phase of metals with overlapping conduction valence bands, the uppermost electrons can freely move around in the crystal structure. Discretization of the energy levels within the energy bands can be observed for cluster size diameters of a few nanometers. Although the crystal structure still resembles the bulk structure, the lattice parameters exhibit already some compression. It is however important to note that, a priori, the discretization in the electronic structure is not necessarily related to strain effects in the particle. Energy discretization is related to the reduction or starvation of freely moving electrons. thus directly related to the numbers of atoms that supply electrons. It is common to call metal clusters exhibiting energy discretization quantum dots. In parallel with the energy discretization, a band gap appears between the valence energy levels and conduction levels. In other words, a transition is observed between a metal conductor to a semiconductor, for which an energy has to be supplied to raise a valence electron into a conduction band. Shrinking the number of metal atoms further, it becomes for the cluster energetically more favorable to form other crystal structures, as shown here for a silver cluster of 38 atoms. It exhibits a truncated octahedral crystal structure. With a change in the crystal structure, the electronic behavior can change further, as we see next for silicon, a semiconductor. The notable features in shrinking the size of a semiconductor to a small cluster are the discretization of the energy levels within the conduction and valence band, and the increase in the band gap that is already existing in the bulk semiconductor. The sensitivity of the band gap to the particle size, and thus its effect on the particle's electric and optical properties, makes semiconducting small particles of great practical interest. We again distinguish between two size scales of confinement. For very small clusters between 10 to 100 atoms, we find strongly bulk deviating structures that are shown here for silicon to be either metallic-like or diamond-like. For semiconducting clusters with atom numbers on the order of 1,000 to 1,000,000, we find a bulk crystal structure to be restored but size dependent, and bulk deviating discrete electronic properties. Semiconducting particles of this size are again coined quantum dots. A critical parameter for determining if a semiconducting particle can be expected to behave like a quantum dot is given by the effective Bohr radius, as determined with the equation provided. It compares if the effective wavelength of the electron is impinged by boundary limitations given by the particle size. In other words, if the particle size reaches the effective Bohr radius or is smaller, quantum confinement can be expected. In the following subsection of this part of the lecture, we will illustrate the impact of quantum confinement by exploring the voltage current behavior of quantum confined structures.